Okay, so hello, ladies and gentlemen, and welcome to another session of EPICentre seminars, the online edition. This is our first session in 2022, so Happy New Year. We will start today with future resilient urban communities in the era of artificial intelligence or AI by Dr. Lee Soon. I'll give a short introduction and then Dr. Lee Soon will share his presentation and tell us what's happening. So give me 1 second. So Dr. Lee Soon is currently a research fellow at UCL EPICentre. Prior to this, he was a research fellow at the Creative Machines Lab in Columbia University. He has conducted his doctorate studies at ETH Zurich. His research focus is mainly in the disaster resilience of modern interlaced infrastructure system. Dr. Lee, we're honored to have you here. The floor is all yours. If you full screen your presentation, we can start then.
All right. Okay. So good afternoon, everybody. So hopefully, first of all, I need to make sure you can hear my voice and see my screen.
I can hear you and I can see your screen, but your screen is not full screen.
Oh, yeah. Okay.
Yeah.
What about right now?
Perfect.
Okay. Okay. So first of all, so Arash, thank you for your kind introduction and Happy New Year to everybody. So like Arash has just indicated, today I'm going to try to share some of my opinions and maybe you can even say some of my misgivings about the latest development in the domain of the resilient urban communities in the era of the artificial intelligence. I mean, this kind of title itself might be a little bit controversial because some people would argue that this kind of so-called era will never come. But okay, so let's try to discuss about it in any way. So because I will be focusing on the hazard resilience of the urban systems consisting of a variety of the modern critical infrastructure systems on the hazard events. So first of all, I'll try to share my reflection on the backdrop in such a domain. Then I'll be focusing on the rapid response. We can say the post-hazard rapid response, which in my opinion can be viewed as a new pathway towards the future resilient urban systems. Then, more recently, this is something we are being focusing on is the autonomous rapid response. We believe that this kind of the latest development in the pursuit of these autonomous agents, artificial intelligence can be leveraged to advance our research in the rapid response. So let's go one by one. First of all, so this is a very, very high level background. This is because despite all of the counter arguments, it's very arguably that our human beings, our world are still undergoing this kind of the very fast evolving urbanization as the data shows in the figure on the left-hand side of the United Nations. And the figure in the right side is definitely illustrative. However, as the data shows that due to this kind of the urbanization, definitely we are witnessing this kind of the population concentration. The population concentration will need to inevitably the wealth concentration, which will then lead to this kind of the risk concentration. Here is a figure taken in the Lujiazui area in Shanghai. So I'm showing this figure just to give you some sense that I can remember when I was very, very, let's say, a freshman in the domain of earthquake engineering. One of my professors in my master studies asked us, supposedly this area was hit by a very catastrophic earthquake. We assume that all the buildings can remain intact. No building will be collapsing, even no building will be damaging. Do you believe that there is enough space for all the people to stand if all of them can be successfully evacuated? This is a good question to ask. Okay, so then I think given by the historical lessons, the vulnerability of the modern critical infrastructure systems has been on full display, I mean, throughout the world. So this is the figure in the middle is, okay, maybe you can identify it's me, but many years ago. So this is a Wenchuan earthquake. I was there on site to engage in this kind of in situ the observation on the seismic damage, and also in particular we were focusing on the power networks, and the damage was so widespread and overwhelming. So given this kind of the vulnerability, I assume that all of us here can be aware that the research focus, let's say, has been shifted to the resilience instead of the robustness alone. So then, therefore, the word of resilience has been a buzzword for nearly 2 decades, ever since Professor Brunel at SUNY Buffalo proposed the idea, or you can say they introduced the notion of hazard resilience of the civil engineering infrastructure systems into perspective. So I would say, so despite the new insights and you can say the success of many of the research, I want to argue that there are still some significant knowledge gap going on up here. So one of them is, in my opinion, is the inadequate knowledge on the impact of the loop interdependencies on the hazard resilience of the modern urban systems. So as you can imagine, when I was talking about the loop interdependence, it goes way beyond the interconnectivity, like for example, the conductors connecting the transmission towers within the power systems, or you can say the pipelines connecting the pumps of the water systems. Think about, for example, not after the earthquake, just right now, the water systems, the pump would need the power from the power systems to function. On the other way around, the power system would use the water systems for the cooling. So it means that if one system was damaged or there are some kind of considerable functionality losses, the other systems will also be significantly impacted, and so on and so forth in turn. So then the water system themselves will also be further, their functionality will also further deteriorate. This can also be the case for the telecommunication systems and the power systems, and so many other examples. Okay. So here, when we are talking about the impact of the loop interdependence, we are still talking about, we can call it the normal operation conditions, just like we're talking right now. Of course, I think maybe very few a few of us will believe that this is really normal. In light of the COVID going on, but at least there is no earthquake hitting us. However, after the hazard, especially those kind of the catastrophic damaging, let's say, earthquakes, so the interdependence among the recovery, not only the functioning in a normal cases like right now, the interdependence between the recovery of a setup of the host of the critical infrastructure systems is even more unknown. However, this cannot be neglected at all. So for example, after the earthquake, if the transportation systems was damaged, like many of the photos taken in 2008 Wenchuan earthquake, so no other restoration can be really push forward. So, and also not to mention the evacuation of so many of the wounded people. So the death toll can be rising very dramatically due to this kind of the stagnant restoration of the road networks. Okay, this is the drawback. So what can we do that? So in the very beginning, we come up with this kind of the last year, we've come up with this kind of the agent-based model on the interdependent road network and power networks. And in particular, we considered this kind of the interdependent recovery of these two critical infrastructure systems. And each of the agents in such a system would be in charge of the restoration of the power system and the road networks respectively, then we are particularly trying to highlight the impact of the interdependence between them on the resilience of the whole integrated two systems. And this is a topology of the two testbed networks. On the left-hand side, this is a power network. We are extracted from the very classical, the IEEE 118 power networks. And on the right-hand side is a corresponding row network embedded in the same area, but it's somehow hypothetical. But although it's fictitious, but per the discussion with many other colleagues in the transportation engineering, they believe that although fictitious, but not fallacious, hopefully, as much as we can. So I just want to highlight some of the very key findings. So as you can find out from this figure, so the purple line means the power demand following the earthquake. So maybe here I also need to highlight that, as you can imagine, of the earthquake, if the community was also hit by the earthquake very hard, so the demand of the community will also drop because, for example, many of the buildings collapse. So for sure, the power consumption will decrease accordingly. So it means that the demand will also not be exactly the same like the pre-shock level, but the demand will also be recovering soon after the shock. So as you can imagine, the demand is, we can say, is something for the power supply to catch up with as soon as possible if the system is resilient. So as you can find out, for the black line, it means that the power network is not dependent. Will not be impacted by the row network. Sorry, the row network will not be impacted by the power network. So it means that after maybe 2 months, the power supply can catch up with the demand. However, if the restoration of the row network will be dependent, and especially heavily dependent on the power networks, there will be a very, very long plateau, as we can observe in the green line. So here, maybe mathematically, I think it's very straightforward for you. So here, the E bridge I means that for each of the single bridge, we will consider the normalized power deficit. Power deficit means the MPD, means that it's the closest the community, the power deficit in the closest community, we will consider this kind of impact of this kind of the power deficit in that community on the efficiency of the repair, or you can say the restoration of such a bridge. So it's clearly, as omega becomes larger and larger and larger, it means that this kind of the impact will be more and more pronounced. So this is a physical measure on the power supply capacity. In the meantime, we also consider for the community, we also checked the percentage of people without power throughout these kind of 4 cases, as we can expect. In the same case, if the restoration of the road network is very heavily dependent on the power network, corresponding power network, there will be a very, very long time for a significant amount of people without any power. So if we want to compute the gross losses, societal losses, as you can imagine, below the green line, the whole area compared to the baseline, we can say, let's say the black line is larger than by order of magnitude. So this is a result by the case study. Okay, so get back to the points we've just made, which kind of lessons we've learned. So as we can imagine, it means that given in light of this kind of interdependence among modern critical infrastructure systems, if one system is severely damaged and cannot be restored in an expeditious way, it means that this kind of the log functionality loss can propagate and potentially trigger a full blown the crash of the whole system for a very long time. And especially, so as we can imagine, for example, the road network is completely decimated and devastated. So if there is no connectivity among those road networks, many of the injured people will die in any way. There is no way, no matter how hard we try, after, let's say, the 72 hours, yes, the death toll will definitely be skyrocketing. So which kind of the solution we can come up with to remedy such a deficiency. So naturally, so also in the framework of the turnkey project, the European Union Horizon 2020, where Dina and Professor Ayana and also Professor Galasso are the leaders up here. So we are making the new argument that one of the root causes for the shortcoming of the state-of-the-art resilience framework lies in the fact that they characterize the criticality of each of the different time windows in an indiscriminate manner. However, in the real world cases, we do believe that in the immediate aftermath of the hazard, the very timely functionality restoration, even just partially, can be very, very critical. So think about, for example, look at this figure. So for example, for this kind of the collapsed bridges, if we can have some kind of the very temporary span, the ramp between these two piles, at least some of the ambulances can get across. So maybe many of the injured people can be rescued and be shipped to the hospitals. This can make a very huge difference. So that's why we argue that the post-hazard recovery phase should be further divided into the immediate aftermath of earthquake, namely the IAOE, and the long-term recovery thereafter. So in such an IAOE, the rapid response should be the action can minimize the functionality losses, or you can say the functionality gap throughout such a period of time. And then we apply such a rapid response-based resilience framework to our road network, the real-world network, namely the transportation systems, in light of their criticality to the resilience for the whole urban community hit by a variety of hazard events. So here we also classified the post-hazard restoration into two different kind of actions. One is a rapid response, as we've already discussed. Another one is just a regular repair, means that they will only go to fully restore each of the damaged bridges. Here, in particular, when we are talking about the rapid response with regard to the road networks, we are talking about the partial repair of the collapsed bridges, namely just we've been talking about here. So for example, to construct the very temporal ramp between this kind of the two piles where the span was completely decimated. So as you can imagine, the rapid response, the repair rate is significantly higher than that of the regular repair. However, its ultimate goal is not to fully repair, but it's just partially repair, maybe to guarantee the very minimum level of the connectivity of those collapsed bridges. So this is another agent we've established. One of the agent A, you can see in the figure, is in charge of this kind of the rapid response. The other two agents will be in charge of the regular repair to the bridges with minor damage and severe damage, respectively. However, I want to highlight that here may be a little bit too complicated to find out, but essentially by doing so, we've established looped interdependencies between the rapid response and the regular repair. As you can imagine, if the rapid response can be delivered in a really expeditious way, it means that, for example, once again, let's go to this figure. So if the trucks need to get across this bridge to deliver, let's say, the restoration on some other water systems or the hospital systems or the any other telecommunication systems. So if the rapid response can be delivered expeditiously, the other restorations can also be accelerated significantly. On the other way around, if the other restoration on the other critical infrastructure systems can be expedited, the rapid response can also be less hindered by the widespread damage. So this is a cycle, or you can say the loop interdependence. For in the negative sense, it means that there could be a slippery slope. So then specifically, we applied such a framework into a real-world road network in Lucerne in France, which is connecting the France to the Spain. It's a ski resort, a beautiful place. And the whole road network in such an area contains a total of 118 bridges, and which also consists the 89 beam bridges, 1 truss, and 28 arc bridges. By the way, so all the arc bridges here are a little bit vulnerable due to their design and the structural characteristics. So essentially, although the road network is not really large, but it still can be viewed as a very heterogeneous one, and the topology is also very unique. So here is some of the result. So on the I'm not sure. I think you can see my mouse. This is a number of the severely damaged bridges where the rapid response has been delivered. So the 3 parameters, 0.75 and 0.5 is used in the figure. Here you can see my mouse. So essentially, it's trying to measure, similar to the case for the result we've already discussed regarding the road network and power networks, shows how interdependent, how heavily the rapid response will be dependent on the widespread damage of the whole systems. So the values is the lower the value is, the more severely the rapid response will be hindered by the widespread damage. If on the other way around, if the parameter is equals to 1, it means that it's totally immune to all the damage of the other bridges. So as we can imagine from the number of the the bridges where rapid response delivered alone, it means that if the value happens to be 0.5, means that the rapid response can be very significantly incubated by the widespread damage. The rapid response is not rapid at all. So after 1 month, only 7 or 6 bridges can be partially repaired. So in this sense, as we can expect, it's one of that helps. It falls short of the expectation we've had, because we want the rapid response can be delivered expeditiously to significantly accelerate the concurrent the full repairs. And also this is a number of the bridges with minor damage in this figure. We've already discussed. So if such a hyperparameter is set to be 0.5, this kind of the rapid response, although it still makes some difference, but it's really not by a very big margin, and it's definitely falls short of our expectation, because here the baseline means that there is no rapid response at all, so it's just a full repair. However, if the parameters was increased to 0.75 and even 1, there is a very huge difference. And here, this is the normalized length of the critical path. Here, the critical path means that from the city center, I think you can see it from this kind of in this area, in the really in the central area, to this point, where we can view it as an exit of the whole network, connect the city to the highway. So once again, so if there is no rapid response, the connectivity of such a critical path can only be restored after more than 3 months. However, if the rapid response is present, depends on which how the value of the hyperparameter omega in the formulas. So if once again, if the omega sets to be 0.5, so it will take around 20 days to restore the connectivity of such a critical path, which is already way better. However, if the parameter goes even higher, then it will only take a few days for the connectivity of such a critical path to be restored, which is very strategically crucial to the evacuation and the rescue and potentially the restoration of all the other infrastructure systems due to the rapid response of the road network alone. All right, so here, but we need to admit that this kind of the case of the omega equal to 1 is clearly too ideal, because for sure, for example, the rapid response, when we can call it the emergency responsive teams, if they want to get across so many of the damaged bridges, so for sure their efficiency, their job will be hindered. So they cannot be immune to those kind of the widespread damage at all. So maybe we can say the omega said to be 0.5 is closer to the reality. Okay, so let's say if it is a reality, let's face up to it. Which kind of lesson can we learn? As we already discussed, so the rapid response, if can be delivered expeditiously, it will definitely helpful and accelerate the regular repair accordingly. Then in turn, the rapid response itself can be less incumbent. However, in the negative sense, if the rapid response cannot be delivered expeditiously, then it's not helpful, and the regular repair will significantly impede the rapid response, so on and so forth. So the irony is we call it rapid response, however, so the rapid response is not really rapid. And when we are facing the massive state space of the modern urban systems. Okay, and here I also want to give you some sense. So why and how to come up with the so-called optimal plan for the rapid response, whether it is very easy or very, very hard. Okay, so let's say supposedly, so we have 118 bridges. So on average, for example, if we consider the epicenter number 1, according to the recorded catalog, earthquake catalog, this is one of the real epicenters in the history. And supposedly there was an earthquake with a magnitude of 7 is occurring here. On average, there will be 19 bridges severely damaged. Maybe 19 to 22 or 23. So let's say if there were 22 bridges damaged, so the trajectory of the whole rapid response campaign would be the factor of the 22. So I don't even know how to count the order of magnitude. So this is a value, the number of the potential trajectories for the rapid response. And I can also give you some sense that in my laptop, of course, this is just a laptop, it's not a supercomputer. The 2000 Monte Carlo simulation runs will take 4 hours. So if we run this kind of so-called brute force search, the exhaustive search, to try all the potential trajectories, then we say, oh, well, maybe which particular sequence will end up with the shortest duration of the campaign. That's the best choice. Then it will take this number of years. So, and we also need to note that this is only a road network with 118 bridges. So maybe for many other road networks, the numbers can be even 10 times, 100 times larger. So then you can imagine. So in this sense, it's maybe we're joking, but it's true that the rapid response can only be rapid after maybe one ice age or whatever. Okay, so are we really going out on the limb? Maybe the answer probably is no, because here we should proudly remember that UCL is the birthplace of AlphaGo 5 years ago, where in the history of the human, the artificial intelligence and in our mankind, this kind of the autonomous, let's say the artificial intelligence trained, the robots, the agent can beat the #1 human players in the chessboard of Go, which is viewed as the hardest game of all kinds. So essentially, so the challenge of our Go also lies in the very, very massive search space, because the chess of Go, the game of Go is too complicated and the search space is too huge. However, Professor Silva in UCL, along many of his colleagues in Google DeepMind, they come up with this kind of the framework. So they use this kind of the look-ahead search to train and generate a pair of the value and policy networks, and use this kind of the value and policy networks to guide their search. And accordingly, because the search was better informed, so this kind of search can generate better, or you can say train the value and policy networks. Then further, they can use this kind of the better neural networks to guide their search to end up with a better result. So essentially, I call it, so by doing so, they really capitalize on the very dark, enormous universe. And all of a sudden, the untrackable, the simulation has become the trackable. and they end up with a huge success. And also all their findings were published on the 2007 Nature paper, and even another paper earlier in 2016 on the first generation of the AlphaGo. Okay, so here I think maybe we don't really have time to get into the mathematics. It's inspired the success of AlphaGo, and we managed to leverage their success and applied it to our case. So essentially, as we've already discussed, so the challenge we are facing is very similar. The search space is simply too huge, too massive. There is no way to run any kind of the brute force search. However, by using this kind of the look-at search guided by the neural network, we train the better neural network to generate a better data set. The better data set can be used to train the better neural networks. Then we can try to somehow dissect the complexity of the very massive universe, let's say yet another universe, maybe not that massive as AlphaGo. So, and also this is a pipeline, the architect of the neural network. We extract the features of the one particular damage state of the raw network into two different layers of the features. One is the component level features, essentially is signaling the damage state of such a particular bridge. And the system level features means that the connectivity among a set of the critical bridges. Then this kind of neural network can be trained to predict the losses, expected losses from such a particular state onward. So first of all, I want to share some of the simulation results. So first of all, so as you can see my screen, so the span-based heuristic, the strategy is the one we've been using in this simulation. So it means that all the severely damaged bridges will be ranked based on their span. So this is can be rationalized because, as you can imagine, the shorter the span is, the easier the span can be, the rapid response can be delivered. So we start from the bridge with the shortest span. It means that ideally we can deliver more bridges in a fixed span of time. However, whether it is not the case, we show that this kind of the span-based strategy is really naive. So although we mean well, however, we really end up with a misery. So then we tried another strategy, means that we rank all the severely damaged bridges based on their betweenness. And then we compare the performance. We can find out that the betweenness-based strategy is way better than the span-based strategy we've developed early on. So it means that the heuristic also matters. Then we use this kind of the framework we've developed to compare with kind of the, let's say, the heuristics based on the domain knowledge, or you can say the human knowledge, namely the one betweenness-based. We can view it as a baseline and a greedy strategy, and also based on human knowledge. We can find out that after just 1 or 2 rounds of the training, for example, the second generation of the neural network, guided by the, used to guide the look-at search, the performance of the rapid response can significantly outperform the greedy strategy. Namely, we can somehow view it as a human player. Then the second generation of the self-learned neural network can significantly outcompete the human players somehow. So then we also here, this is a one particular test run. So because there are 19 bridges in the very big, immediately following the shock, then we applied the betweenness strategies and also the second generation of the neural network, the look-at search, to generate the sequence. So as you can imagine, for the betweenness-based strategy, I mean, very straightforward. So the 19 bridges, they will always go to the bridge with the highest betweenness, then go to the second, go to the third, go to the fourth, until the 19th among the 19 ones. Then we compare the second generation of the neural network. We see how its sequence would be looking like. So first of all, maybe we can take a look at the results. As we can find out for the betweenness-based strategies, there were a lot of plateaus associated with the whole trajectory, means that they face a lot of obstacles. However, for the second generation of the neural network, although there are some short plateaus, however, it almost perfectly circumvented all the obstacles from the existence of the other damaged bridges. Okay, so now let's go back to check out what's the difference. So the difference is very, very straightforward. So very interesting. So as we can find out, so for the first 3 bridges, the 2 strategies, their sequence are exactly the same. They both go to the bridge with highest betweenness, then go to the second, and then go to the third. The third bridge is the bridge number 99 is here. However, for the greedy-based strategies, we can call it the human knowledge-driven strategies. They will go to, namely, they will just go to the bridge with the 4th highest betweenness, namely the bridge number 1. So this is the shortest path it will take to reach there. Obviously, it will go through many of the other damaged bridges, so their efficiency will be significantly reduced. However, for the second generation of the neural network guided the search, they will go to the bridge 111, which is here. So this is a shorter path. Not only there are zero damaged bridges, there is no damage indeed associated with such a shortest path. And more importantly, not only they will go to this bridge, in sequence, they will also go to 116, 117. So as you can imagine, when they were trying to deliver this kind of the rapid responses, there is 0 obstacles. So that's why in such a period of time, they delivered the rapid response to all the very critical 3 bridges in just a couple of 1 week. However, for the greedy-based strategies, even for many of the bridges, only 1 bridge will take more than 10 days, which is significantly a lack of adaptivity. So essentially, although this is just one of the single test run, so although we can find out some of the difference of the behavioral pattern of the decision makings, it means that by self-learning, this kind of the artificial intelligence driven strategies can purposively execute the harvest of the low-hanging fruits just in order to achieve the long-term goal, or you can say the long-term rewards, maximize long-term reward to fulfill the optimization objective we've already set up. Namely, so here we can say that our long-term strategic optimization objective is a minimization of the duration of the whole campaign. So then we can compare the duration of the whole campaign was reduced almost by half. Okay, so this is just a test run. So, and also we have uncovered the different patterns associated with it. So somehow we can conclude that by the self-learning, so the artificial intelligence without the human intervention and without human knowledge can significantly outperform, you can say, the very, very the sophisticated, the human knowledge-based strategies. And also, I also need to highlight that this kind of the development is not very, very relevant and helpful to drive and to deliver the smartest decision makings, but also can also be crucial, strategically crucial to the post-hazard rapid response of the modern communities hit by the variety of different kind of hazard. For example, in Fukushima, 2011. So they were very, very, let's say, the long-standing the nuclear leakage. So no human beings should be sent there to deliver any kind of the restoration or rapid response. So in this sense, this kind of the grouped robots, recovery robots, can do the job instead of human. However, if they want to do their job, they need to plan by themselves without any human knowledge, because the humans are not there. We don't know the situation. They need to make the best choice given the current state they are facing. So if we cannot do that, so it means that the the loss of functionality will also make the entire environment inhabitable and inaccessible to human beings, yet another slippery slope. However, if this kind of the autonomous grouped robots can really do this as human beings, so this can be a very, very key to the resilience of the future urban communities facing a variety of different disruptive events, even including the pandemics. Okay, so I'm sorry, because due to the very tight schedule, so I wish I convinced some of you that regarding the following issues. First of all, why rapid response? Because the loop interdependencies, due to this kind of the loop interdependence, any of the functionality or loss of any single infrastructure systems can propagate and can potentially trigger a very long time the crash or shutdown of the whole systems, and it can be very, very devastating to the resilience of the whole community. So the rapid response could potentially serve as a key to extract us from that predicament. Okay, so then what are the rapid response? As we've already discussed, for the raw networks, we employ this kind of the partial repair of the collapsed bridges as a mechanism for the rapid response. However, it can go way beyond the partial repair, even go way beyond the physical rapid response. For example, the coordination, the traffic coordination, we can call it the societal, the rapid response can even be more interesting and can be more relevant and useful. This can be definitely something we need to explore in the longer run. And one rapid response, clearly, we've already said that IAOE, immediate aftermath of earthquakes, or you can say IAOH, immediate aftermath of hazard. So the rapid, or you can say the rapidity is a soul of the rapid response. And how, as we've already illustrated and highlighted, that by preemptive the training through the deep reinforcement learning, we can train an oracle. We can view that kind of the very smart and a very advanced neural network as an oracle who can tell us which action should be better, which action should be, worse, or the worst, and by means of the locata search. Okay, so by answering to the questions why, what, when, and how, I think somehow we've generated some new insights, and we also generated some of the issues we need to be talking about right now. Thank you.
Perfect. Thank you very much. As usual, if anyone has any questions, please feel free to unmute yourself or type it in the chat, and I will read it aloud. And as usual, I will start with some questions. Okay, resilience. We'll get back to the definition of that, but can you go back to one of the networks that you were showing with the epicenters? And you were saying that let's have the one with the network itself. So one slide after this, 26, yes. So you're saying that the second generation decided to go back, while the human beings, let's say, decided to go to the other side of the network.
Yeah.
Are you prioritizing the bridges and the locations? Have you told the system that this area is more important? Because why I'm asking this is like, okay, it makes sense that you start building and coming to the center. So you connect A to B, let's say south to north.
Yeah.
But imagine like the AI is going backward and there is no one living there. So he is making a bridge, but it will affect, let's say, 100 people. While if we connect and prioritize south to north, we will affect millions of people. Have you mentioned this to the system that, okay, look, this bit is more important than the other bits? Okay, so Arash, a very, very excellent question. So indeed, because like I said, maybe we don't have time to get into the mathematics. So essentially, in such a particular case, our optimization objective is indeed, we call it the GWL, the gross weighted losses. So gross means that across the whole campaign, and the weighted means that for each of the bridge, so we have different damage state, right? Everybody can understand. No, 1 means no damage, 2 means moderate damage, and 3 means that severely damaged, however, rapid response delivered, and 4 means that severely damaged and no rapid response delivered. So, however, we also multiplied such a damage state with the betweenness. So essentially, that's why we call it the betweenness-based strategy is a greedy strategy, because it will always go to the bridge with the highest betweenness
and let's go to the second and go to the third. So Arash, in particular regarding to your question, so here we're not considering the population, we're just measuring the criticality of each of the bridge with by their betweenness values. However, so in this sense, if we are going in a greedy way, so this is exactly the pink color, the shortest path we'll do. We'll go to the bridge number 1 here with the 4th highest betweenness. However, if we go there, you will go through this kind of the path where many of the other damaged bridges are remaining there. So your job will be significantly hindered. However, if you go in this way, keep in mind, the 111, 116, 117, namely these 3 ones, as you can see, they were not really a very, they were also very, very important. They were namely the 5th, 6th, and 8th. So it means that instead of going to the 4th, we go to the 6th, 5th, 6th, and 8th. Then we get back to the other bridges, which are also accessible and also maybe critical, relatively speaking. So by doing so, by avoiding the harvest of the low-hanging fruits, they can fulfill the long-term objective. So this is the argument we're trying to make. So maybe, although I'm not an expert on a game of Go at all, I mean, even I don't know anything about the Go. However, I know, for example, when we are talking about AlphaGo, the AlphaGo can also do something similar. So instead of going to pick the very obviously, so-called obvious, the good actions, they're purposely doing something very strange. However, in the longer run, they believe that they laid some trap for the opponent. Then the trap can walk into it. Then in maybe 20 steps later, he can completely destroy the opponent. This is a pattern. So I would say it's comparable to each other.
Yeah, I read about that as well, that the human player was surprised of the move, and the move of the AlphaGo seemed very stupid, but it built up in like 20 afterward moves that suddenly it made sense. Now I'm getting it. I'm looking at, I call the left one the human decision, the right one the AI, and I can see, yes, they are a priority because the human goes back to them as well. But the AI goes from another perspective, and definitely let's say the repair time has decreased by 2 times, I think, if I remember. Yes. So 120 and 60 days, which is an important one. And you mentioned that the AI understands the damage state as well. So, okay. And
it's a feature, yes. So yes, when we are trying to, because definitely, as we imagine, so if the AI doesn't know the damage state, it cannot make any prediction, right? Like the AlphaGo cannot see the chessboard, right?
Yes. And okay, so you advertised the system which is better than Monte Carlo simulation, which was taking decades, let's say, while the artificial, and what is let's say, what is the end point of this? We want the AI to consider every single possible scenario and keep it in its mind that when the incident happens, gives us an instruction that, okay, allocate repair team to this point, and carry on. Or based on that, we will realize that these bits are the problematic bits, so we can allocate some resources for repair close to them. What is the final goal of this?
So yes, Arash, you are exactly right. So both are legitimate. In one hand, because that's why I use the word preemptively. So because the neural network, you cannot, Arash, you cannot train an AlphaGo after the game has started with Lee Sedol, right? They did this in London for years, I think. Then they use AlphaGo in the Seoul, the capital city of South Korea, then play the 5 tournaments with Lee Sedol. Then they win 4 of them. So similar to us, we cannot do this after the earthquake, in particular, when we don't know when and where the earthquake will come. However, you can train the neural network based on the significant amount of the random scenarios. So then the neural network can capture the dynamic. Then as soon as the earthquake hitting us, then we know, for example, what the optimal trajectory could be looking like. And also accordingly, like Arash, you are definitely right. We can also maybe do another preemptive planning. So it means that some of the bridge, if we believe that they are really critical, so we need to preemptively, for example, allocate some resources or dispatch some teams, for example, a center near them, something like this. Both are legitimate, I would say.
Okay, interesting. So it is a live system. At least the goal is to have a live system that when the earthquake strikes, considering the training that we have done the AI, in few seconds, it tells us this is the plan, let's do it. Okay, it's case sensitive as well.
Yes, otherwise you need to run this kind of brute force search, will take ages, many years later, then we find out the best solution.
Yeah, and then this can be connected to the water supply, the power supply, and one by one you can have priorities that, okay, I know there is access for the road to this power supply, so you can fix it. If there is no access and there is no prediction in the next 60 days, you don't need to waste your time. Okay, the way that these systems work together, I think we don't have it right now with all of these departments and stuff. It's very hard to manage it. So this will be a significant help to the disaster management.
So I'm not sure Dina is here. So indeed, Arash, maybe we need to keep talking afterwards. So we want to apply. We believe that this model can be even more powerful in terms of the interdependent systems, because now we only have a very small road network. However, if we are looking into the interdependent systems, the system can be more useful. However, like you've rightly pointed out, for many of the systems, the data is confidential.
Yeah, I can imagine. Yes, they're essential systems and like high security systems.
So they will never share
internet,
you. The topology, for example, London will never share you the real topology of the road network power systems up here.
Yeah, they say that the future wars and stuff will be turning off an entire city by accessing and hacking their system. So very important not to give access to everyone. But yes, research-wise, we wish that we could see those.
Go ahead. Sorry.
If there is no other questions, I have some more, but due to the limit of the time, I will ask them later on. So yes, Dr. Lee Soon, thank you very much for the interesting insight to what is the future of prediction. Seems like someone has a question, please.
Yeah, sorry, Professor. My question was that actually you said that you are going to use this proposed system after the event, and it is basically it has a lot of features that it is feeding the system, and these features are, as I understand, damage states, and these damage states are directly related with the event itself. And without knowing the event, the damage states that you are feeding the systems will be uncertain, and this uncertainty is going to be exposed all the system that you have. Have you studied about that? Like, have you checked what is the uncertainty about this and about the damage states and how it will affect the final result? I just wanted to ask that to Professor Soon, Dr. Soon.
Okay. Thank you for your question. So essentially, I can view it from the artificial intelligence perspective. It's some kind of the perfect, or you can say the complete information and incomplete information. So if we are we analogize it into AlphaGo. So AlphaGo is a very classical game that the information is always available, and it is a very complete information all the time. So at this stage, you are totally right. So we assume that we immediately after shock, we know the damage state of each single bridge. This is assumption. However, definitely it's fair to argue that maybe this cannot hold true for many of the cases. Then it means that we are facing some kind of the incomplete information. So in this sense, if we really want to do that beautifully, maybe we need to introduce another model similar to the Bayesian stuff. So based on the very limited information, whether or not the neural network can still make a reasonable prediction based on the limited information, or maybe they need to develop some belief based on the limited information. Then they can extrapolate the limited information into the whole system. So this is something worthwhile to pursue, I definitely admit. But at this moment, we assume that the information is complete.
Okay, thank you. Actually, I have another question, if it is
Please.
possible. Again, it's about the features.
Yeah, please.
And it is about the question that Professor asked. I don't remember the name, sorry. Arash, I think. And it was about like, did you train it according to fragility or vulnerability? Did you train the system according to fragility or vulnerability? Because if you train according to fragility as like damage states or stuff, without informing the social side of it or economic side of it, of the case, it will end up something like, as you see, like to go back to the shortest one, but maybe it's not important. Did you train it according to fragility or vulnerability?
Yeah, so yes, okay. So essentially, so far we are focusing on the fragility, not instead of the vulnerability, because it's like you said, so for many of the socioeconomic measures, sometimes the data itself is not available.
Yeah, okay.
Yes, and also that's why, so at this moment, so that's why we assume that is our objective, optimization objective is simply the duration of the campaign, the time of the whole campaign. We didn't consider the total economic losses because sometimes this data is not available.
Thank you. Thank you, Professor. Thank you.
No, thank you. But we wish that the model itself, the architect means that the network is scalable and adaptive. If we have, if we have the data, yes.
Yeah, I know it's it is fully related with the data, and I just wanted to know if you Thank you.
Yeah, excellent discussions. Thank you.
Perfect. Our students in coming weeks, they will learn how to develop fragilities and how to translate that fragility to vulnerability. So this is where those fragilities and vulnerabilities with that many hours of analysis comes into play. You have a bridge and we want to predict how it will react under different scenarios. Dr. Lee, thank you very much. Again, very interesting discussion. I will just share my screen for a second and I will be talking about what is coming afterwards. So we had the resilience urban communities in the era of artificial intelligence. Next week on 2nd of February, we will have improving fire risk assessment in historic building, the case study of Notre Dame by Dr. Augustin Guibault. So I will see you next week.
Okay, take care, guys. Thank you.
See you later.
Okay, thank you. Bye.